In this lesson, we are going to look at graphing polynomial functions. So the more information we can get to graph this, the better. So things that we can look for are intervals of increase and decrease, critical numbers where there's maximum, minimum values, concavity, any points of inflection, and that will help us graph this. So here we have a function 3x squared minus x to the power 3. One value I could find, let's use blue. One value I could find is the y-intercept. So I could just put in 0 and I get a y-intercept of 0, 0. I want to find where the graph is increasing, decreasing, and perhaps any maximum or minimum values. So I'm going to find the first derivative. And then we'll set that equal to 0 and we'll factor. I see a common 3x. And then we'll solve for our critical points. So we have two possible turning points at 0 and 2. So I'm going to make a table of values here and look at the intervals of increase and decrease. And we'll put our factors down the sides, and then we'll find the value of that y prime to see if it's increasing or decreasing. So pick a number less than 0. We'll get a negative result, so it's decreasing in that interval. Increasing between 0 and 2, and then we'll pick a number bigger than 2. Negative results, so decreasing. So these are our intervals of increase and decrease, and also able to identify a local minimum at x equals 0 and a local max at x equals 2. Okay. Another piece of information I want to know is, are there any points of inflection and where is the graph concave up or down? So in order to do that, we'll do the second derivative. Set that equal to 0, factor out a 6, and we have a possible point of inflection at x equals 1. So I'll do an interval table at that interval. And here we're looking for concavity, any change in concavity, which will determine our points of inflection. 6 is always positive. So I get a positive result, which means it's concave up when x is less than 1. I get a negative result that tells me the graph is concave down when x is greater than 1. And because we have a change in concavity, that means that we have a point of inflection at x equals 1. Okay, so I may want to put in some, find some exact numbers. So if I put in 1 into the original function, I get a value of 2. And with our critical numbers, likewise, I'll do the same thing here. I have a local max at 2. The y-coordinate that goes with that is 4. And I have a local min at 0. And the value that goes with that is 0. So now we can start sketching the graph. So we'll just put on the important points here. So 1, 2, 3, 4. Put some scales on here. So we have a y-intercept at 0, 0, which is also a local min. We have a point at 2, 4, which is a local max. We have a point of inflection at 1, 2, which is right there. And then I know when x is less than 1, it's concave up, and when x is greater than 1, it's going to be concave down. So it's going to be concave up to here. 0, 0 is a turning point. concave up to here. Then the concavity changes, concave down, and then concave down. So the points I put on here were my local max at 2, 4, my local min at 0, 0, and I have a point of inflection at 1, 2 where the concavity changes. All right, let's do the next example. So we have x to the power 3 minus 3x plus 4. So we'll go through the same process. My y-intercept would be 0, negative 4. We'll find the first derivative so that we can determine our intervals of increase, decrease, and local max and min. Set that equal to 0. I'm going to factor out a 3 and then factor a difference of squares. So we have possible max mins, critical points at x equals 1 and x equals negative 1. So we'll make our interval table and look at those intervals. Put our factors down the side. You don't need to include the 3, but it's a good habit to get into because sometimes that constant is negative and it will change the direction of the graph. So pick a number less, oh well, 3 is always positive, so let's put that in there. Negative, negative, positive, increasing, negative, positive, negative, that's decreasing, and then positive, 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 that's increasing. So we have a local max at x equals negative 1. We have a local min at x equals 1. Okay. So I'm going to sub those back into the function, and I get negative 2 when I sub in negative 1, and I get negative 6 when I sub in 1. Second thing I want to find is my second derivative, so we can look at concavity and any points of inflection. So we get 6x, set that equal to 0, x equals 0. So that is a possible point of inflection. So we'll do an interval table with that value. So negative, positive, concave down, concave up. So there is a change in concavity, so there is a point of inflection at x equals 0. And so x, when x is less than 0, it's concave down. When x is greater than 0, it's concave up. So we can start sketching. So let's put some marks on here. Okay, so what points do we have? We have negative 1, negative 2 is a local max. 1, negative 6, let's move this up a bit, is a local min. We have a point of inflection at 0, negative 4, which is also our y-intercept, 1, 2, 3, 4. So that we know it is concave down to 0. So concave down to here, that is a turning point at negative 1, negative 2. Continues to be concave down to 0, negative 4, which is a point of inflection. Then it becomes concave up to 1, negative 6, which is a local min, and then it's concave up. So that is what my final graph looks like. I'm just going to label this. Let's take that out there. So that point, local min is 1, negative 6, local max is negative 1, negative 2, point of inflection is 0, negative 4. So those are just graphing polynomial functions, getting as much information as we can so that we can create an accurate graph. Okay, some questions will ask you to sketch given the derivative, or given a derivative, find the original function. So in this question, it gives us a graph and it wants us to sketch the derivative. So the original function is a cubic function. right? It's power 3. So I know that my derivative is going to be a quadratic function power 2. Okay. Critical numbers or turning points occur here and here. That's where the slope of the tangent is 0. So we've got a critical number x equals -2 and a critical number at x equals 0. That's when the slope of the tangent line, f prime of x, is 0. So I can put those points on my grid here at 0. What else do we know? We know that when the function is less than 2, so let's do f prime of x. So I can see here that from here to -2, the function is decreasing, which means the slope of the tangent would be negative there, and it's also decreasing here. So that tells me the slope of the tangent when it's less than -2, so it's going to be, the slope of the tangent is going to be negative when it's x is less than -2 and when x is greater than 0. And then the slope of the tangent would be positive between 0 and, or -2 and 0, because the line's going up. Oops, don't need that. Okay, so what does that mean for the graph? That means that my derivative will be negative. I'll just put a negative here. When x is less than 0, or less than -2 or greater than 0. I'm just going to erase this green. Oops. So that we can see the original function. Well, it doesn't want to do that. Okay, so let's just do it in red. So it's going to be negative here and here. And then between 0 and -2, the derivative is positive. So it's going to be above. So that's what my graph would look like. So I'm looking at the turning points to give me my critical points on the derivative. So that's where the value of f prime of x would be 0. And then I'm looking at where is it increasing. That would be positive on the derivative. And where is it decreasing? That would be negative on the derivative. Okay, let's have a look at this one. So we have f of x is quadratic. So it is a x squared, so I know the derivative is going to be linear. Okay, so what do we want to find? Well, here is a turning or critical point. So f prime of x, the slope at that point would be 0 at x equals 0. It is increasing or having a positive slope when x is less than 0, and it is decreasing or having a negative slope when x is greater than 0. So it's going to be positive before 0 and negative after 0. So what does that look like? So here is my critical point at 0. I'm just going to erase this point here. Oops. Okay, so there's my critical point at 0. That's where the slope of the tangent is 0. It's going to be positive before that and negative after that. So I've got a linear function that is positive before 0 and negative after 0. Okay, in this question, it's the reverse question where we have given the derivative and we want to graph the original function. So we're going to reverse what we just did. Okay, so in this question, the derivative is linear. So I know the original must be a quadratic. I'm going to look at where is f prime of x 0 at x equals 1. So right here. So if the slope of the tangent is 0, then that would be a turning point on the original function. So somewhere on this value for x is my turning point. So I'm just going to reset. Okay, before this point, the derivative is negative when x is less than 0, and it is positive or above 0 when x is greater than 0. So where the derivative is negative, right, it has a negative slope, means it must have been decreasing in that interval. And where the derivative has a positive slope, it must have been increasing in that point. So it doesn't really matter where you put the turning point, but I know it has a negative slope before that point, and it has a positive slope after that point. So that turning point can go anywhere because we don't know the equation of the original function. So we can just put it anywhere on there. Okay, in B we have a derivative that's a quadratic. So that means that the original function must have been a cubic function, right? So 1 power greater. So that's what we're looking to draw. What do we know here? Well, here is where f prime of x is 0 at x equals 2. And what do we know before that? Well, we know that f prime of x is positive when x is less than 2, and it continues to be positive when x is greater than 2. So what does that tell me? That tells me that it's always increasing. So my cubic function will always be increasing. I also know that at 0, here, this would be a point of inflection because the slope of the derivative is 0. So before that point, f prime is decreasing when x is less than 2, which means that it would be concave down, and f prime is increasing after x is 2, so that means it would be concave up. So my graph at 2 would be the inflection point, it would be concave down before 2, and it would be concave up after 2. This being the point of inflection, it is always increasing, so it's going up from left to right. Okay, in this question it gives you some information and then we just have to sketch. So f of 3 and f of 5 equals 0. Those are x-intercepts. So we have an x-intercept at 3, 0 and 5, 0. F prime of x is negative when x is less than 4. It is 0 at 4, and it is greater than 0 or positive after 4. So what does that tell me? So f of prime of 4 equals 0 is a critical point or a turning point, because that's where the slope of the tangent is 0. It is negative when it's less than 4, so that tells me it is decreasing, and it is positive after 4, so that tells me it is increasing. And then f double prime of x, or the second derivative, is positive for all x's. That means that it is always concave up. So I'm going to have a point at 3, 0 and a point at 5, 0. I'll put those in red. I have a turning point at 4. So somewhere here there's going to be a turning point. I'll just put it here. It's concave up always. So concave up to there, it turns, and then it continues to be concave up. So it would look something like that. So it doesn't really matter where that turning point is as long as it's below those x-intercepts. Okay, similar question here. We have an x-intercept at -4. We have a y-intercept at 8. We have turning points at -1, 10 and 3, 1 because f prime of x is 0, so that means that they are turning points, local max and local min. F double prime of x equals 0 at 1, 3. That is a point of inflection. So when the second derivative is 0, that would be a point of inflection. And then f double prime of x, or the second derivative, is negative. So negative when x is less than 1. So when the second derivative is negative, that means that it's concave down. Okay, so let's see if we can sketch this. So what do we have here? We have an x-intercept at -4. We have a y-intercept at 8. We have a point of inflection, or a turning point at -110. So here we have a turning point at 1,3. 3,1. 3,1 is a turning point, and 1,3 is a point of inflection. 1, 2, 3. So those are the points that I know. I know when x is less than 1, it's always going to be concave down. So it's going to be concave down to here. So I pass through the x-intercept, turning point at -110, continues to be concave down, passes through 8, continues to be concave down. At 1,3, the concavity is going to change because that is a point of inflection, so it's going to be concave up. And then at 3,1, that's a turning point, so it's going to continue to be concave up after that. So probably want to put in these labels, local min at 3,1, local max at -110, x-intercept at -40, y-intercept, and then my point of inflection at 1,3. And then we have the finished graph.